So I'm interested in really, really low mass white dwarfs. So stars that have 20 or 30% of the mass of the sun. Our universe, our galaxy, isn't old enough to make a star evolve all the way through its life to get to one of these really, really low mass white dwarfs. And so the only way you can form a white dwarf with such a low mass is for it to have a binary companion. So this is a kind of a cartoon illustrating this soon-to-be white dwarf, so sort of red giant star that's expanded its envelope and started dumping mass onto some companion. So the reason we're interested in looking for these low-mass white dwarfs, are one of the reasons that that we're most interested in looking for them is we're looking for really, really close binary systems, because they're preferentially found in binaries. The only way to make one of these really low-mass white dwarfs is to have a really close companion that eats a lot of its mass. So sort of the I like this quote from Tom Marsh that low-mass white dwarfs need friends. They need to have some other either compact object or other star-like star in orbit around it, in a binary, for it to lose mass. Like I said, the galaxy isn't old enough that a single star can evolve to a white dwarf that has 25%, 20% of the mass of the sun. So you've got to have a binary companion. So not only do you usually have a binary companion, but you usually have a really close binary companion. So we've been involved in a survey that's been led by McCremmon-Killick, who was a former student of Don's, and a guy he worked with at Harvard, Warren Brown. And what they do is they look at a low-mass white dwarf, they take a spectra of it, and they watch and see if that spectra is getting red-shifted or blue-shifted. And that'll tell you the binary parameters of the system. It'll tell you the orbital period. And so most of these that we see have orbital periods of about 7 hours. Some 2 hours, some 12 hours, but about 7 hours is the average. Yeah?
Do these binary systems just look like one point of light?
Yeah, usually we just see 1 point of light. So the nomenclature astronomers use is a single-line binary and a double-line binary. And a double-line binary means you could resolve both stars, light from both stars as it moves. And in all of these cases, it's usually just a single-line binary. We just see the one. That's a good question. Obviously, there's a companion that's contaminating some of that light, but it's just usually too compact for us to see.
So we never know that they were binaries if we didn't look at the spectroscopy.
Exactly.
But most stars are binary.
Yeah. Something like that. It's about 50-50. I mean, people don't know for sure, but yeah. So about 2/3 of stars in our galaxy are in binaries. That is to say, well, that's too convoluted. All right. So I'm going to give you guys 2 examples of systems we found here, and why I find them personally very satisfying and interesting to work on. So if you looked at them with the 82-inch. With our instrument, it's just a CCD. It's just a camera. So it's almost like an SLR. You shove a camera up to the telescope. All the telescope does is get you more light. It's a bigger surface. It's a bigger collecting area. So you get more light, but really all you get out is this picture. And this is a false color image, so it's taken through a bunch of filters. So you get that the hotter stars are blue and the cooler stars are red. But essentially, the star that we're interested in, our white dwarfs are almost always hotter than other stars that we see in the field. So the white dwarfs are always going to be these blue dots, even though it's kind of hard to tell in the room because there's so much light. But that's a star we're interested in. And so Warren and McCremmon went to the MMT. I think I'll have a picture of that in a minute of what the telescope is. It's a 6.5-meter telescope in Arizona. So it's really big. And it does really good radial velocity work. And you can see that over time, so this is folded on the phase. So 0 to 1 is 88 minutes. But if you look at it running in time, each one of these spectra is where those lines are red-shifted or blue-shifted. Since it's a white dwarf, all you see are hydrogen lines. But you see the hydrogen lines, you're getting red-shifted and blue-shifted and red-shifted and blue-shifted. And there's a period to it. And if you fold it on exactly that period, you get this. And it's repeated, so you can see it with clarity. So oftentimes you'll see, I'll show a couple plots like this. But what this is this is 88 minutes, or whatever the orbital period of the system happens to be. And you can see all our data fits this trend really well. So this thing is in a whopping, this is 800 kilometers a second, peak to peak. It's really fast. This thing's moving around at like 0.1% of the speed of light. These two stars are going around each other. So this system is an 88-minute period binary. So in 88 minutes, to have two stars that are that close together, it would fit within the never mind. I don't remember the exact value of what that is. But the point is, there's one low mass white dwarf we see, and an unseen companion that's tugging that white dwarf around some center of mass, and the white dwarf is getting closer and further away from us. So I've gone and looked at this system with Argos, and I'm gonna spend some time on this because this is a lot of plots. But hopefully, after what you did this week, it'll start to make sense. So ignore this side for a second. I should just black that out and focus on this right here. So these black points right here, this axis is in time. So this is 0 to 10,000 seconds. So this is almost 3 hours worth of data. Each one of these black points is the light from the white dwarf. And this is just a comparison star in the field to show that it's relatively constant. But there's a lot of scatter. This is a really faint star. I think the star is like 19.5 magnitude or something, which is just quite faint. So this is about the error bar for each one of these points. But you can kind of see there's a little bit of a trend in the data. And so if I fold at the orbital period, which is 88 minutes, this is what you get. This is what the light curve of that star looks like. So there's a real clear trend where at half the orbital period, you get this real big sinusoidal trend in the data. So if you take a Fourier transform, which is what this is right here, so this is frequency versus amplitude, you see that at about 1.5%, there's a really, really strong signal at 43.99867 minutes. Okay, does that make sense, everybody? That's what I've marked with this little green line right here. Okay, so that's the peak of this in the Fourier transform. So this Fourier transform is we're just trying a bunch of test frequencies and seeing what the amplitude of each one of those frequencies is, how well it reproduces the data, basically. And so we've got more data than shown right here. I think I've got a total of like 20 hours worth of data on this star. And the biggest peak in the data here is at 43.99867. Well, the orbital period that we saw from the radial velocity is 88 minutes. So half that orbital period is 43.999. And that's what we see, 43.99867, plus or minus some value. Okay, so we got a really strong signal at half the orbital period that we saw. We have another strong signal at exactly the orbital period. So we got this peak right here in the Fourier transform is at 88.0045 minutes. And that's really, really close to the orbital period. In fact, it's within the errors of the orbital period. So we determine the orbital period by watching the star get redshifted and blue shifted, right? That's this period right here. That's 88 minutes. Does that make sense to everybody? So what we're seeing is light variations from the white dwarf at the orbital period to about 0.6%, and at half the orbital period at much higher amplitude, at like 1.5%. Could you guys think of what either one of those things could be? So if you had two stars going around each other, how could you make the light of one of those stars get modulated at that orbital period? So the three really, really big ways you can do it. Two of them I don't think you're ever going to guess, but one of them maybe you can guess. Okay, so there's four. Yeah, that's one of them. So in eclipse, you would see a big dip at either phase 1 or phase 1/2. Okay, so we don't really see an eclipse in this data, but you'll see an eclipse in a second. I'll show you what that would look like. What else could you think of would cause brightness variations at the orbital period of something? So a third body. So there are already two bodies in this system. There's already a star and another star that's tugging it around. Yeah, there's three body systems. Yeah. So
side by side from our point of view.
Sorry.
Side by side from our point of view.
Side by side from our point of view. What does that mean?
Going perfectly, you could say parallel from our point of view. We were looking straight at them.
Yeah, so that would eclipse. That would be an eclipse that we'd see if they were right.
No.
Oh, if they're both side by side.
Yeah.
In a way, that's sort of one of them, but but it's a little more nuanced than that. So, so when you look at the moon, and the moon is new, I'm pointing because you can't, whatever. Let's pretend like the moon was up right now. It was dark. Yeah, we were in like Siberia or something, not getting hit by asteroids and meteors, whatever. And you looked at the moon, and the moon was new. Let's say the moon were new today. It's not. But if it were new, could you see a new moon? Like, let's say it's 2 days from a new moon. Could you see it? There would be like that little sliver. But you can also kind of see the rest of that moon, right? So like you see the sliver that's being illuminated by the sun, but can you also kind of barely see the rest of it? So why can you see the rest of that? So that's light reflected off the Earth onto the moon. So that's Earth shine. Okay? So in binary star systems, you can have one star that's much brighter than the other star, and you can actually see a reflection effect off of one of the stars. Does that make sense? You can actually see that light get reflected. So that's one of the most common ways that you see light modulated at the orbital period of 2 stars in a binary. And I spent a long time talking about that. That's not actually what's causing either one of those effects, but that's the first is eclipses, the second is that. The third way is similar to what you're talking about you seeing them both. But really what's happening here is that the white dwarf primary that we see, we say it's the primary because that's what's contributing like more than 99% of all the light. That star is actually being tidally distorted. There's another mass in the system that's really massive. That's what's tugging it around and causing it to come back and forth towards the Earth. And so here's a cartoon of that. So that white dwarf is no longer spherical. It looks almost like a teardrop, but you can think of it like a football. That's what the ellipsoidal. It's like an ellipse. And so when we see it this way right here, there's 2 faces, I like to think. There's a fat face to that white dwarf, and then there's a skinny face. And when we see that fat face, we see more surface area of the white dwarf. So when you're seeing more surface area, you're seeing a brightness increase. And when you're seeing less surface area, you're seeing a brightness decrease. And you see that, oops, you see that twice per orbit, right? Because you see, so you can think of seeing 4 sides of that white dwarf. You see this side once, and you see that side once. Does that make sense? So that's happening at half the orbital period. So that's why you see these. So from here to here is 1 orbit, and you see 2 peaks. Okay? So you also see that these peaks aren't symmetric, right? So one of them is brighter than the other. That's because superimposed on that, there's another signal at the orbital period. And that's causing another increase. That's a little less, that's a more sort of subtle effect. But it's actually an effect that comes out of special relativity called Doppler beaming. And the source is moving so fast that the opening angle of the photons coming from that star are being beamed towards us when it's moving towards us, and they're actually being beamed away when they're moving away from us. So the fact that the thing is moving so quickly, it's beaming its light towards us. And this is one of the first, this system right here was one of the first times anybody's ever detected that effect from the ground. And it's a really whopping effect. I mean, it's essentially the difference in these 2 amplitudes here. So that's purely coming out of Einstein. That's purely coming out of special relativity right there. So that's really cool. So that's the 4th way you can have. That, like I said, that happens in very, very rare cases. And since this system's moving so quickly, since it's moving at like 1/10 of a percent of the speed of light, that's why we see that asymmetry. Does that make sense? All right, cool. So that's, yeah.
So we don't see this other companion, it's really dark. What could it be to be so dim?
Yeah, that's a good question. So, so when you look at this star, it's getting tugged around really vigorously. And the amplitude of this tugging, let me back up a little bit. We can look at this white dwarf. We see the white dwarf, and we can fit models to it, and we can make a guess to its mass. And we assume its mass is something like 0.17 times the mass of the sun, or 17% of the mass of the sun, or 0.17 solar masses, or something like that. So we have a good guess at what the primary star is that's getting tugged around. The amplitude of these radial velocity variations can tell us what the mass is, what the total mass of the system is. Okay? And since we know the mass, or we think we know the mass of the primary, then we can have a guess at the total mass of the system. Does that make sense? But that value actually depends on the inclination to the system. So if we saw that system edge on, then that value, we would know exactly. We don't know the inclination. We don't know how the system, so these two stars are going around each other. We know they're not going like this because we don't see them eclipse each other. But they could be going around each other like this. They could be going around each other like totally edge on or face on to us. Yeah.
Does the nature of our data tell us that, or no?
No, there's really no way we can know that unless they eclipse each other. We can try to constrain it, but it's totally, it's really hard to determine. So anyway,
So velocity is the nature of the component of velocity is the direction of our side.
right.
So they could either be going real fast, almost directly toward us, or really, really fast, and not that direction toward us, but the component along our side is still bigger.
Yeah. So the absolute minimum mass of the companion is something like 1.1 solar masses. Okay? And so that's if the inclination is like 80 degrees. That is, it's not quite edge on, but it's just slightly. Because we know it's not edge on because they don't eclipse. Yeah?
How would you be getting any data for face-on velocity?
Yeah, so the system itself, the star is getting redshifted and blue shifted. Just the star. Does that make sense? So we do see the red shift and the blue shifts, and it's pretty, it's whopping. It's like. Oh yeah. So you're right. The radial velocity amplitude would start to go down. The worse, because all of that motion is going to be tangential. It won't be radial, right? And so we wouldn't see much of a radial velocity signal. Yeah. So the other way to answer that is to say the only way we would be able to detect it is if the companion had a huge mass, like 100 solar masses or something, right? So, yeah.
So by aggregating all this data, could we start to detect which ones have what inclination?
Well, the inclination is sort of. I like that you guys are troubled by us not knowing that because it's a huge uncertainty. It basically goes as cosine theta, or cosine the inclination. So it really starts to run away at low inclinations, at like an inclination of 10 degrees or something like that. The way I kind of go about this is our models shouldn't be too bad about what the radius of this star is. And these ellipsoidal variations can tell us the inclination of the system using the radius of the star. And so that's how we can sort of start to constrain the inclination. That's sort of the best way about it, yeah.
So what's your most likely path?
Well, I don't know. There's no way to. So the most common inclination, if you just randomly looked out at any particular direction, the most common inclination is 60 degrees. And so at 60 degrees, the mass of the companion would be something like 1.45 solar masses or something like that. It would be, let's just say it would be 1.5 solar masses, would be sort of the most common value for the companion. Do you guys remember what a limiting mass is for a white dwarf? 1.4 solar masses. Chandrasekhar mass. So if this thing has a mass 1.5 solar masses, could it be a white dwarf? The companion did. No. And so, in fact, the most likely scenario is that the companion is actually a neutron star. And that's why we don't see it, is because it's a neutron star. Does that make sense? Because if the companion, the companion has to have 1.1 solar masses. It can't have any less than that, for sure. If it were a 1.1 solar mass white dwarf, it would have to have some temperature, probably at least 6,000 degrees. I don't know. It would be interesting to constrain that, but we would see that. We would see that in the data, and we don't see a companion at all. All we see is one star. It's just a single line binary. So more often, the most likely scenario here is that it's a neutron star. That.
Is there a limiter for neutron stars?
Yeah, that's more theoretically constrained than observationally constrained. Rob Robinson would say 2.6 solar masses. Some people have claimed 3.2, but certainly no more than 3.5 solar masses for a neutron star. Nobody understands the equation of state of a neutron star, so it's really hard to estimate that. All right, cool. So that's actually the second most exciting system I think we've found. this is by far, in my opinion, the most exciting system we found. So I should have shown this a little earlier. This is the instrument we use, Argos, and it literally is just a camera at the prime focus of the 82-inch telescope. And this is what our friend here, this 12-minute binary, 065, we say J0651 because that's where it is in right ascension and declination. So back in March of 2011, Warren and McCremon targeted this star with the MMT. And actually, this is, I'll start here because this is sort of like the discovery data. So this is the MMT, a 6.5-meter telescope at Whipple in Arizona. Yeah, so this is time in days, and this is radial velocity amplitude. And you can see this white dwarf is getting whipped around really, really quickly. And so the first 2 exposures they ever got of this star just so happened to sample the maximum difference in radial velocity amplitude. And the thing shifted in radial velocity by like 1,300 kilometers a second, which is outrageous. I mean, that's 0.5% of the speed of light. I mean, it's ridiculous that 2 stars would be going around that quickly. So we didn't know the binary period then, but we kept looking at it, we kept looking at it, and we kept watching the star get red shifted and blue shifted. And so we folded in all our data. And you see it fits really well. So the system is composed of a white dwarf that we see and another one that we don't see so well in the spectra. And they're getting shifted around by 1,300 kilometers a second. I don't know why I went backwards. All right, so this is a cartoon of that system. And it just so happens that these stars are really, really edge-on. So we know the inclination really well, which is good. And we see these big, deep primary eclipses, and then these shallower but still pretty deep secondary eclipses. And we see these ellipsoidal variations like we saw in the last star. And there's also a slight but pretty serious asymmetry. So it's got all of these effects. It's got everything but the reflection effect.
So is the smaller dip when the small star is in front of the big star?
Yeah, so here is the primary dip, where this is the big star that we see. That 96% of the light from the system is coming from this star right here. And so when the smaller star, which is smaller in radius but actually bigger in mass, because that's kind of how white dwarfs work, when this smaller star in radius blocks the light from the primary star, we get these big, deep primary eclipses. And vice versa, when this, if you rotated these 180 degrees and had the smaller star up here, you get these secondary eclipses when the bigger star and bigger radius eclipsed it. This system is extreme. So this is to scale. This is the Earth and the Moon. And then this is these two white dwarfs to scale. So they're about a third of the distance from the Earth to the Moon, apart from each other. So this is 75% of the mass of the Sun packed, within a third of the distance from the Earth to the Moon. So these stars are super close together. And we did a lot of ground-based follow-up because we wanted to measure this effect that I'll describe in a second. But we got time on the GTC, which is a 10.5-meter telescope, 10.4 meters in the Canary Islands. We got time from Gemini at Mauna Kea in Hawaii. Got more stuff from the MMT. So the shape of these eclipses that you see, their duration and also their shape can put really good constraints on the physical parameters of the stars in the system. So you remember at the beginning of the talk I was talking about how most white dwarfs are like 60% of the mass of the Sun packed into a radius the size of the Earth. Well, to scale, these 2 stars are much bigger than the Earth. In fact, the low mass star, the 0.26 solar mass one that we see, is probably closer to the radius of Jupiter. And then this smaller star, it's still a little bigger than the Earth, but it's got about half the mass of the Sun packed into that volume.
Is that to scale?
Yeah. So these are sort of 1 sigma error bars on the radii, and the star itself that we see is a little tidally distorted, so it shouldn't look perfectly circular. Does that make sense? Yeah. So that's all I'll say about that. So here's the real exciting reason why we wanted to keep watching this system. So this is the primary eclipses of the system that we saw back in April of 2011. And so we can do some model fits to the data. We can fit a light curve model. So we can sort of we can say, OK, we've got a half a solar mass and a quarter of a solar mass, and we can describe the radii of the two stars. And we can say, OK, these eclipses happen at exactly this time. And that's sort of what this dashed line is representing right here. So back in April of 2011, the eclipses happened at that exact time. We kept watching the system. In January of the following year, you can see the midpoint of this eclipse has shifted by about 4 seconds from when it did in April of 2011. All right? So in April of 2012, I'm not going to go through all these, but you can see that the midpoint of these eclipses is changing. It's changing dramatically. All right? So what could that tell you about what's happening here?
More carbon dioxide, oxygen are being burned than previously?
No. Yeah, but that's sort of the next step. I mean, what is this saying? Yeah. Exactly. So the orbital period is actually getting shorter. That's why these eclipses are happening sooner and sooner. And it's not a linear relationship. It's actually a quadratic relationship. So that means the effect goes with time squared. So instead of being a straight line, our data should look like a parabola. And that's exactly what we see. So O minus C just means what we observe, when we observe the eclipse to happen versus when we expect it to happen. So this dashed red line is when we expect it to happen. And you can see that line, the mismatch there is growing. And that's what this dotted line is right here. That's when we expect the eclipses to happen if the orbital period isn't changing. And you can see that the orbital period is changing pretty significantly. So I assume you osmotically got the gravitational radiation from the title. Yeah, so there's a reason why we expect the orbital period to be shrinking. And that's because these two stars are really, really close together. So Einstein's general theory of relativity says that mass bends space, right? So that's kind of what this top cartoon is showing. Even light gets bent by mass distorting space, okay? So both of these stars have mass. They have a lot of mass in a really, really concentrated space. And so both of them are bending space. But they're also going in orbit around each other. So you can kind of think of them like bobbing up and down in the wake of each other's mass. And that's exactly what's happening. So if you wiggle a charge, what happens? If you accelerate a charge? Yeah, you have a break in those field lines, and it propagates out. That's radiation, right? So that's electromagnetic radiation if you accelerate a charge. That's exactly what's happening here, except instead of a charge, it's mass. So you're accelerating a mass. And it's giving off radiation. It's giving off gravitational radiation. So that radiation is actually taking energy away from the system. So there's energy in the orbit. There's angular momentum in the orbit of these two stars. There's a hell of a lot of it. And that gravitational radiation is taking away some of that energy. And so it's causing the orbit to shrink closer and closer together. All right? So gravitational waves, or gravitational radiation, is something that we've known about for about 100 years now. But we've never directly detected it. We've only indirectly detected its effects. And that's because it's a really, really small effect. So this value h is a change in length over length. So that's sort of the displacement that wave causes compared to some distance. So the only way you can really measure a gravitational wave is to see something get deflected by that wave. So these are really just like ripples in a pond, sort of propagating out through the fabric of space. They're really, really subtle. So that value, this delta L over L, for this system, which is the second strongest source of gravitational waves we know of in our universe, is only displacing space over some distance by 10 to the minus 22. So if you use units of meters or something like that, that's basically like displacing, if you had two atoms that were a meter apart, you'd have to displace them by a billionth of a femtometer, or a billionth of that atom. So it's a really hard measurement to make. So the only way we're ever going to make that measurement is to make this L, to make the distance between our two detectors really big. And so what we're trying to do is send detectors into space so that we can have hundreds of thousands, millions of kilometers distance between the two detectors so that we can see them both sort of bob up and down by a gravitational wave. The first actual indirect confirmation that gravitational waves existed came from a binary pulsar, so two neutron stars going around. Yeah?
How fast do these
it should be at the speed of light. That's what all the theory says. But like I said, we don't know for sure because we've never actually detected them. But I wouldn't bet my career on, but I'd bet somebody else's career. It's probably at the speed of light, or very close to it.
Why the speed of light?
That's just how it falls out. Yeah. I honestly don't know off the top of my head. It's a good question. So we watched, just like we watched our 12-minute binary back in the mid-'70s, Holson-Taylor found a pulsar, which is a really rapidly spinning neutron star. The thing was spinning, it's like milliseconds is its orbital period. So you get a really, really accurate clock. And they watched that clock for a couple decades, and they saw that, sure enough, the orbital period was shrinking by 0.076 milliseconds a year. And that fit exactly with the prediction from general relativity for gravitational radiation. So that won him a Nobel Prize in 1993. So that was the first time this effect has ever been detected. And it's only been detected in a half dozen other systems. And they've all used neutron stars or pulsars. So this is the first time anybody's ever been able to do that in the optical. So I'll sort of show a different. This is like the one that was on its side here on the right, that O-C diagram. I kind of turned it back over and showed all the different. We've gotten data from all these different telescopes on the mid-eclipse times. And this gray line is what we expect from just gravitational radiation. We expect more than 1/4 of a millisecond each year that the orbital period is going to shrink by that much. And our observation right now is actually a little faster than that. It's still within the air, but it's right on the cusp of being faster than you expect. So we published our data up to here saying that, yeah, we saw the effect of gravitational radiation. It was really exciting. We got some good press out of it. But I'm actually more eager to make this measurement, which is sort of the fact that the orbit's shrinking a little faster than we'd expect from gravitational radiation. I won't ask why you guys think it's actually changing faster than gravitational radiation, but I'll see if we can get there. So remember how I said the stars are one of the stars is tidally distorted? So it's being distorted because tides from the other star are being pulled. So there's a companion and a primary. That companion is it has a lot more mass than the primary we see. And it's drawing tides on the primary star we see. So a similar analogy is the Earth and the moon. So you guys know we always see the same face of the moon, right? So there's always the same face of the moon is always facing the Earth. What causes that? Yeah, that's tidal locking from the Earth. So the Earth's tides on the moon are keeping that lunar face locked. The same thing is, or a very similar thing's happening here, where these two stars want to be locked together. There's a tidal bulge that's actually being locked from the tides in the system. So as gravitational waves take away energy from the orbit's shrinking. But the stars want to be rotating at exactly the orbital period. So in order to stay rotating at the orbital period, what has to happen? Does the rotation rate of that star have to change? Yeah, right? Yeah, it's got to compensate with the orbital period. And so the rotation of that star is actually going to spin up. And that's going to take even more energy out of the orbit. And this red line, which was what we observe, is actually getting pretty close to what we might expect from tides in the system. So we're seeing energy from the orbit being lost from gravitational waves and from tides in the system. I show this. This is another diagram that I made. But instead of using these really complicated eclipses, so this is what my models look like, my light curve models. And they fit the data pretty well. But I can also fit the data by just fitting a series of sine waves to it. So I can take a Fourier transform of my data. And this is a Fourier transform of my data. So this red dot is the half orbital period. This is the orbital period. And this is just a bunch of harmonics of the orbital period. And that actually does a pretty good job of reproducing these eclipses. Does that make sense? So I'm fitting a bunch of waves with harmonics of the orbital period. So I'm doing sort of a Fourier analysis, and I can come up with a really similar answer that I did with with a light curve model. Does that make sense? Maybe not. That's I don't know, kind of esoteric, but it's just saying that it's a sort of a model-independent way to do it. But I'm also trying to tell you guys that we use Fourier transforms a lot. It's a really powerful tool for time series and data analysis. That's really all I think I have. This is you know, sort of the obvious question is, what's the future of this system, right? The orbit's obviously decaying, and it's decaying really rapidly. It's losing something like 1/4 of a millisecond every year. And the orbital period's only 765 seconds. So at some point, the orbital period's going to shrink. What do you guys think is the future of this system? So do the two stars just come together if they did that? Or what would really happen?
After a while, the gravitational effects of them on each other will overcome the effects. I don't know.
Would the larger one start making more mass than the smaller one?
Boom. Yeah. So exactly what she said. Let me sort of give you a cartoon of what that is and what she said. The larger one, which has the smaller mass, is going to start dumping its material onto the smaller one with more mass. I hate the way that works out, but sort of a better way to visualize that, we can draw little equipotential surfaces. So this is a bad cartoon that I drew up, but I'm hoping it kind of makes a sense. Let me see. The bigger circle here, this is the one with more mass, and this is the one with less mass. And where they are right now, you can imagine you could drop some test particle, like right here. It's going to stay in that potential well. It's going to stay in that gravitational potential well. But at some point, there's going to be a little saddle. There's going to be a connection point where a test particle right here no longer stays in that star, and it starts to dump. And that's when mass transfer starts. That's when you get accretion starting from the less massive star to the more massive star. So the point when the system really starts to get funky isn't when the orbital period goes to 0. It's actually when the radius of the less massive star is able to start dumping material onto the more massive star. Does that make sense? And that happens when the orbital period's about 7 minutes. And that happens in about 1 million years, which is really, really soon on astronomical timescales. That's pretty fast. So we're not going to see it in our lifetimes. But at some point, the less massive star is going to start dumping its mass on the more massive star. So what will happen when it's done with that process? So this star right here, the more massive one, has half a solar mass. The less massive one only has about 1/4 of a solar mass. You guys remember that magic number we were talking about earlier, the Chandrasekhar mass? What's the total of that mass? It's under the Chandrasekhar mass, right? So this thing's not going to blow up, probably. So it'll probably just be some kind of freaky-looking white dwarf, subdwarf hybrid. Maybe it'll have dredged up some of the carbon from the more massive star. It'll probably have a helium-dominated atmosphere. It could have you could get temperatures hot enough. So this is mostly helium. This star is almost entirely helium, the low mass one. And at some point, some of that helium could get hot enough to where it could thermonuclearly detonate. So this is what you call a 0.1A supernova. But it probably won't even have enough mass to do that. So yeah, it's really not. We're not really sure what's gonna be the future of this thing.
That final mass transfer stage, I don't know much about this, but it might be fast.
Yeah.
Because as the big fluffy star loses mass, what happens to its radius? It grows.
Yeah.
What happens to the radius that's losing mass? It accelerates. So once
Yeah.
it starts losing, it goes blah. And so I don't know how fast that can happen, but maybe in a matter of minutes.
Oh yeah, I don't even know.
You can dump tenths of solar mass from one to the other and maybe blow up
So nobody really, this whole process is very unconstrained. And the biggest factor, the biggest variable in everything is the ratio of the masses of these two stars. If these stars had about the same mass, then sort of all bets are off, and mass transfer may not even happen. But this star is massive enough that it'll probably be able to efficiently take mass off of the lower mass star.
Another thing to think about is the angular momentum of the system.
Yeah.
Can be conserved. So either mass is going to fly off with a really high velocity, or it's going to be really fast spinning, or both.
Yeah. Yeah. Cool. So I'm hoping that, so this is an object, I know we haven't fully talked about what will happen over spring break, but we'll definitely be looking at this system over spring break to try to get another few points on this diagram. And it'll be cool. It's really fun to watch because I mean, things are happening on very short time scales. You see a deep eclipse every 12 minutes. And so it's really satisfying to watch. Cool.
All right, well, thanks, David.
Yeah.
All right, well, if you guys have any more questions that you think of over the weekend, just let us know next week, and I'll see you for the lab.